Okay, welcome back, everybody. We are very happy to have Maitreyi Kulkarni from Bonn, and she will tell us about continuous associahedron in type A.
Great. Thank you so much. Thank you for inviting me to give this talk. Great to be back at ICTS. Okay, so yeah, I will. So first of all, this is joint work with Jacob Matherne, Kaveh Mousavand, and Joe Brock. So how this started is Kaveh, the second author, was working on classical associahedron or realization of classical associahedron, and that was in terms of representation theory. And Joe Brock, the last this author, he was or she was working on the continuous or representations of continuous quiver or representation of real line, which is also equivalent to continuous cluster categories. So, but there was no okay, so in classical case, associahedron holds a lot of information about cluster categories or cluster algebras or representations of quivers, but there was nothing like that. There was no associahedron for the infinite case, and so Job and Kaveh kind of started working or thinking about what could be done. And then when Kaveh was visiting Bonn, we kind of started talking, and then we all got together and started working. So I'm telling this because this is how I'm going to tell the story. First, I will tell you about classical associahedron. So there are many realizations of this associahedron, but I will tell you first the combinatorial one. Then I will tell you the one that Kaveh was working on, that is a more representation theoretic, which allows us to kind of generalize it to the infinite case or the continuous one. And then I will tell you a little bit about continuous version. Okay, so the associahedron Kn classically is n minus 2-dimensional convex polytope. The vertices are, so if you take a word, an n length word, then vertices are ways of inserting n minus 2 pairs of parentheses inside it. And edges are one application of associativity. So for example, if I have length 3 word, I can either put parentheses here, or I could put parentheses on BC, and this is exactly one pair of, one application of associativity. So this is the associahedron for n equal to 3. For n equal to 4, now we have 4 letters, so A, B, C, and D. And then you can have 5 of these. And maximal number of parentheses is 2 here, because, so, I mean, if I didn't have anything just around AB, then I wouldn't know the order for C and D. So I do need 2 pairs of parentheses here. And this is where this n minus 2 comes from. So I will just quickly draw K4. It's a pentagon. It will have 5 of these ways of putting parentheses. And you can see that at each edge is just one application of associativity. Okay, right, so this is a pentagon.
Sorry, can I ask, I'm a bit confused as to how you went from the top one to the left one, which is A, B, and C, D. Yeah, from there to there, how did you go?
Right. So, I mean, here either you're, the outer parentheses kind of becomes this one. So this is because you're first applying, you're first applying with, you're multiplying by C and then D, but here you're applying C, D together and then this.
But how is that an edge? I mean,
you call AB as X, right? Basically, you're calling AB as X. When you're doing XCD to XCD.
Yeah. XCD to X and CD. Okay, I see. Okay.
Yeah, so thanks. Like this, like if I just call it X. Then...
Yeah, thanks. Yeah.
Thanks, Apurva. Okay. And then K5 is a little harder to draw, so I'm not going to draw all of everything, but what I will say here is if you start with just one vertex, then you will have three three applications of associativity. So each word will be, each vertex will have three neighbors. So similarly, if I go next, I will have, two more because one is already here, and so on. So this is how K5 looks like. I will show you like here. So here is a picture in 3D. So each vertex is connected to three of them. But okay, so how I have drawn here is like a graph, and now you can see that, okay, at least at K5, I can look at it for long enough and see how to rearrange all of these vertices and then make it into a polytope, or see that it's a convex polytope. But this might not be possible as n becomes larger and larger. So it would be nice to have coordinate version of this. So it would be nice to have coordinates for each of the vertex of this associahedron to see it. So that's why there are many realizations of this associahedron. There's a paper by okay, so let me write this down. The paper is called as Many Non-Equivalent Realizations of the associahedron, and the paper is by I don't want to miss the spelling, Ceballos-Santos-Ziegler. Okay, so and there are really just many non-equivalent realizations of this associahedron if you're interested. I will give you one of those. So how do I go from like a word or some way of putting parentheses to getting coordinates? So here is one, and this is done in using what is called, so these trees or these graphs are called rooted planar binary trees with n leaves. So here, because I have, so n is 4, there are n leaves. So these are rooted planar binary trees. So to each word, I'm going to, so here are the 5 ways and here are the 5 trees. Maybe I can show you from the beginning how I got the one that here. So for each A, B, C, D, so I'm considering this this way of parentheses, and then so I will have 4 leaves. Because I'm doing AB first, AB is in a parentheses, I'm going to join A and B first, then I will join C to it, and then I will have D to it. Okay, so this is how the tree goes. Then what I'm going to do is I'm going to label the rest of the vertices that are not leaves. And I'm going to name them in the following way. So let's start with A. I go up the tree and see which is the closest vertex that is not named. Let's call it VA. I start at B, go up and see which is the closest one that is not used. So it's this, I call it VB, and so VC. Okay, and now to get the vertices, or sorry, to get the coordinates here, what I'm going to do is I'm going to look at VA here. Okay, so we look at VA, go down the tree and see how many number of vertices are on the left and how many are on the right, and count them. So there is one vertex on the left of VA, one on the right that are connected to VA going down. So the entry corresponding to VA is 1 times 1. Similarly, I can do this for VB. I go down and see that there are 2 of them on the left, 1 of them on the right. So the entry is 2 times 1, and so on. So this is how I get 1 times 1, 2 times 1, 3 times 1. The coordinate which I get is 1, 2, 3. This is how. So from a word, I've gotten coordinate for each of the tree here, and if I plot those on, so here is the. Sorry,
so you're going to keep the product notation here, or are you going
to? No, you don't have to. I just didn't write it, but yeah, okay. This is really just, I mean, 3, 1, 2.
Okay, great. Yeah.
Yeah, and you really just plot these points in R3. And as you can see, all these points or the coordinates of this point sum to 6. And this is not a coincidence. So in general, this realization of Kn sits inside this hyperplane, where the sum of the coordinates is n choose 2. And yeah, so for K4, this is the realization. It's a pentagon. It's not a regular pentagon or anything, but it's a pentagon, and it sits in one plane. Okay, but as you can see, this, I mean, we or at least we didn't see like a nice way of generalizing this into an infinite associahedron. How do you start with an infinite such an infinite rooted tree? So I'm going to tell you about 2 more realizations that we use that were reasonable enough for us to generalize into infinite or continuous associahedron. So the first one was given by Arkanni Hamed by Yan in 2018, and this was a physical realization of of an associahedron. So it's called ABHY associahedron. I will not tell you about this construction too much because this is more physical and they build it in some kinematic space. But the same, so I will just write that this is a physical realization. But the same associahedron was now by Kave and friends was given in terms of representation theory. So ABHY associahedron was it was the same realization, but just given in terms of representation theory, which is let me write this down. This was in terms of representation theory. This was the first version came out in 2018, but they kind of kept updating the version. So the latest one is 2021. And because this is like more mathematical, this is the one that I understand, I'm going to tell you this. And now, because of representation theory, Lincoln diagrams come into picture. And so in retrospect, this was only for type A, this realization. But now because the Lincoln diagrams came into picture in the second one, this is for all types. I will tell you about this realization in a minute, only for type A.
There's a question, Maitreyi.
Yes.
Can you hear him?
I cannot hear, sorry.
Hi, I have a question about what is the realization of an associahedron? How do you define it, and how? What does it mean to say there are 2 realizations are equivalent?
Yeah, so I just mean like the objects that are used to. So you know how like here we started from like a word and got some coordinates corresponding to each of the vertex, and then actually found how to draw the edges. Like we took the convex hull of this, and then sorry, can you hear me because my internet?
Yeah, I can hear.
Okay. Yeah, so you know how we found the coordinates and found convex hull, and that gave us this associahedron. So something like this, so some way of getting coordinates of the associahedron and actually seeing it in some Rn. So that is what I mean by realization. And so by ABHY associahedron, I'm saying the 2 realizations the same is because like the physical realization or the objects that they used to make this into a real object, like a seeable object, are kind of like correspond in representation theory to what I'm going to talk about.
Oh, okay.
So yeah, so they're kind of like related, but I don't want to talk about the physics side of it, so I will tell you about the math side.
Right. So in ABHY, there is an embedding and they do some computations over that. So you're saying like in the representation theory, one can get such an embedding into something. Yeah, okay. Yeah, thanks.
So so right. So now in the second one, you can actually do this for.
There's one more question, sorry.
Okay. Yeah.
I have a question. Do we know of a realization where all the vertices lie on the sphere? Is that possible or it's not possible?
Yeah, I'm not sure. Yeah, that's a good question. I'm not sure.
Thanks.
Yeah.
Hello.
Okay. Yeah.
So what is the difference between A type and B type?
What is the difference between?
A type and B type.
I think they mainly, I think these people mainly did this for simple. So I don't know if B is actually what they consider. I think it's mainly for simple. So ADE, I think. Yeah, maybe I should say simply list. Is that okay?
Yeah, go ahead. Yeah.
Oh, okay. Okay. Yeah.
Thanks.
Yeah. Right. Okay. And so, I mean, okay. So then here, when I talk about representation theory, I will tell you like how this associahedron holds this information or combinatorial information about cluster categories or cluster algebras and so on. Okay. Now why continuous? So this was one of the this is something that I mentioned earlier, but Igusa, Rock, and Todorov have been working on representations of continuous quiver or real line. Or continuous cluster categories. And there was no such associahedron built for continuous cluster categories, which will hold combinatorics of all of this. In physics, though, Arkani, Hamed, Her, Salvatore, and Thomas, they do have an infinite dimensional associahedron, but this was defined as a limit of the classical associahedron. So another thing we were wondering that can we just mathematically give a definition of infinite dimensional associahedron without having to take a limit, and where all this finite ones can be embedded in the infinite dimensional. Okay, so this was kind of the motivation for all of this. So let me first tell you about the representation theoric realization. I'm going to cheat a little bit. So I'm not actually going to tell you the whole representation theory. First, I will build this associahedron only combinatorially, because if I have to start with representation theory, it will be a lot to take in. So instead, I will give you all the objects combinatorially, and then at the end, I will tell you objects corresponding to what representation theory object. I think that will be useful. Okay, so we start with a type A quiver. Let's take A2, for example. I want vertex from 2 to 1. So this is my A2. We build a new quiver. We take positive or non-negative integer many copies of Q like this. So this keeps going. The vertices are labeled I and J, where I tells you which copy of quiver you're in, and J tells you vertex of the quiver. Now we already have like arrows of the original quiver inside each of the copy. There will be additional arrows. So like for every arrow from J to K in Q, we will add an arrow from K to J in the new quiver. but from ith copy to i+1th copy. So like we kind of make this quiver connected like this. Okay, and this keeps going on the right hand side. So from a quiver, we have built an infinite quiver. Okay, so what we're going to do now, we are going to put dimension vector on the first copy of Q. Okay, so I'm going to say this, but it's okay if you don't totally understand it. Like, I mean, it's a bit technical. All I'm trying to do now is from this infinite quiver, I'm going to take a small finite copy of a quiver, or small part of this quiver, so that I know where this associahedron lives. Okay, so I'm doing this dimension vector stuff only to see what is the dimension, like what is the vector space where this associahedron lives. That's all I'm going to do. Okay, and to do that I need dimension vector. So I'm going to put on 0j, so let's say 0, 2, I'm going to put 1 at j. So the dimension vector is going to have 1 at 2, and then at every vertex that can be reached in Q op from 2, I'm going to put 1. Okay, so Q op now is this quiver. I put a 1 here, but I cannot go anywhere from 2. There's no arrow going from 2. So I'm going to put 0 on 1. So the dimension vector is going to be 0, 1 here. And on the other hand, this is going to be 1, 1, because if I put 1 here, I can actually reach 2 just by going through the arrow. So the dimension vector is 1, 1. Okay, so okay, somehow we have decided to put 0, 1, and 1, 1 on the first copy of Q. Now, what comes next is important. So fill the rest of the dimension vectors using what is called mesh relation. So what is a mesh relation? Whenever you see such a diamond in our infinite quiver, we are going to say that I want x plus y to be equal to z plus w. Okay, and this is going to be, the mesh relation is going to be used later also. Okay, so now you don't see any diamonds here. So what we kind of have to do is we have to put zeros here. I mean, we complete the diamonds to get, sorry, we put zeros to get to complete the diamonds. I mean, if you had A3, you would see diamonds already in the infinite quiver, but anyway, at the end, you will have triangles. So you just put zeros at the end for any quiver. So, okay, so this is, so you get the idea. And now I know that I know 3 other vertices. So what is the dimension vector that goes here? Well, it will have to be 1, 0. Okay, and then now I have 3 in this diamond. I have to fill in the 4th one. And okay, so I'm just going to do this. This one is going to be 0, -1. This is going to be -1, -1. This is going to be 2, 1, or sorry, -1, 0, 0, 1, 1, 1, and so on. So as you can see, the dimension vectors are getting repeated, but okay, that's okay. We don't have to worry about that right now. Okay, so next, now that I have dimension vectors on all of this, remember the whole point was to get some finite quiver out of this infinite quiver. What I'm going to do is I'm going to cut this part of the quiver where the dimension vectors are non-negative. Okay, and I'm going to call this quiver I plus. Okay, so just the 3 vertices at the beginning. Then I'm going to construct another quiver, I, finite quiver from it. So I'm going to go just 1 step ahead in each row. So my I is going to be this quiver. Now it has 5 vertices. And I'm going to call it I. Okay, so now we have, from this infinite quiver, we have a finite quiver. I plus has 3 vertices, I has 5 vertices, and the vector space that the associahedron lives in is indexed by elements of I. So for A2, our associahedron lives in R5 because, sorry, going back, I have 5 vertices in I, 1, 2, 3, 4, 5. Okay, so that was all the point of this dimension vector business. Now you can forget about it. So now we have a vector space where this associahedron lives. Okay, so now let's actually define the associahedron, right? So let xij be the coordinates of V. So they are indexed by I. So we have 5 variables for our our example of A2. Now to define the associahedron, we need 2 things. We want a tuple C underline, which is okay. So Cij, where ij is only in I plus. So let me write this down and then I will tell you in the example what I'm doing. So this is any collection of positive integers. And c-deformed mesh relations. Okay, so what am I doing with the C is, so I've drawn a simpler picture. So now we had this infinite square, we cut out a small part of it. This, the gray or the black part is I. I have these extra zeros just to make them into diamonds. Our I plus was these 3 vertices, right? x02, x01, and x12. So for each of them, I will have a Cij, and I'm going to put Cij here. So let me write this here. So C02, I'm going to put in the first diamond, C01 in the second, and C12 in the third diamond. And c-deformed relations look like following. For every such diamond where I have xij on the left, Cij, I put the constant in the middle, and okay, whatever it is in the W. Whenever I see such a diamond, I want xij plus W should be equal to Cij plus Y plus Z. Okay, so xij plus W should be addition of everything in the middle. So this is giving me a system of equations, right? So I have 3 systems of, 3 equations, system of 3 equations on the left in my example. I take x02 plus x12 should be addition of x12, c02 plus 0. Okay, don't worry about the 0. So this is how I get the first equation. The second diamond gives me the second equation. Third diamond gives me the third equation. So this is the system of equations I get for A2. What is the point of this putting these Cijs is only because if you put zeros for any of the C's, you start getting something degenerate. So like your associahedron, I mean, if everything goes through the origin, you might not have anything interesting going on in the associahedron. That's why you want some positive to like skew it properly to get some good associahedron. So yeah, so just to avoid degeneracy, we are putting these C's in the equations. Okay, and now the associahedron is just the collection of non-negative solutions to these c-deformed mesh relations. Okay, so yeah, so if you solve these, fixing the C, so the definition depends on the C. Then the non-negative solutions of this system of equations gives us a BHY associahedron. Okay, any questions? Yeah, I can answer some questions if you have any. Right, so our associahedron lives in R5. There are 3 equations, so it's going to be in 2-dimensional plane in R5. I mean, if you just look at this, I mean, it is still not easy to see what the associahedron is. But here is a theorem that will that is helpful. This was again by Kavi, Mousavand, and friends. Each facet of the associahedron is given by vanishing of exactly one coordinate of V. Okay, Let me read the second one, and then I will go back to the example and explain what this theorem is saying.
Sorry,
Now-
question. There's a question.
Mhm.
So in the previous page, you mentioned that the solutions to this system of equations gives you the associahedron. How is it connected to the bracketing of the letters? How the solution is connected to the bracketing of the letters?
So this is not exactly coming from the bracketing. This is coming from the quiver. So
Oh, quiver.
we are starting with the quiver and building this association.
Okay. Thank you.
Okay, and then the second point is, if G is a face of this associahedron, consider the set ij of I. Remember, these are just the coordinates of the vector space, such that G lies on the hyperplane xij equal to 0. If this set is compatible subset of I haven't told you what a compatible subset is, but just bear with me for a minute. If this set is compatible, then this gives a face of G, and all compatible sets appear this way. Okay. So what is this saying? Let's go to the example again. So it's saying that suppose I choose to put x10 equal to x01 equal to 0, and I plug in x01 equal to 0 in this system of equations, what I'm going to get is an edge of the pentagon. So spoiler alert, this associahedron corresponding to A2 is going to be a pentagon. It's not, again, I'm drawing it like a regular pentagon, but it's not. I will show you exactly how it looks in a few minutes. But just to tell you what is going on, if I put x01 equal to 0, what I'm going to get is an edge of this pentagon. If I know that x01 and x02 form a compatible set, then I equate them to 0. I equate the compatible set equal to 0, and what I get is a vertex of each vertex of this pentagon or the associahedron. So this basically tells you, this allows us to get vertices of the associahedron. Okay, so you find the maximal compatible set. You set all those variables to 0. What you get are vertices. So this is already telling you coordinates of vertices. Let's do an example. Let me tell you what compatible is. So actually, I'm going to tell you what incompatible is. So two variables, x and y, are incompatible with each other. If this happens, if you have a rectangle where x and y are on the two corners, or y and x are on the two corners, left and right corners, not top and above, not top and bottom, but left and right vertices. Okay. For example, here, let's take x02 and let's see if we can find incompatible ones. I can, right? So this is a rectangle in this quiver. So x02 is not compatible with x12, so I cannot use them together to get a vertex. Another one is another rectangle is this one. Okay, so x02 is incompatible with x11, so I cannot use them in pair to get a vertex. What I can use is x02 with x01 or x02 with x22. Okay, so that's what I'm going to do. I put x02 here and whichever it was. Remember, these two are compatible, so I can use them. So x02 and x01, I put in 0 for them, and I choose C's to be 1, 1, 1. Okay, now given this information, I solve the system. I get 1, 2, 2 as the rest of them. So the point I get in R5 is 0, 0, 1 to 2. I'm just reading these coordinates. That's all. Okay. The same thing I can do here. I can put these two form a compatible set, so I can plug 0 for them. I solve the rest of the system given that all my C's are 1. I get this point in R5, and so on. So I find all the compatible sets. There are 5 of them, so I get 5 points corresponding to each of them. I plot them again. So here's a subtlety. This is still a point in R5. How do I see something in R5? So what they found is if you just project this everything into the last 2 coordinates of R5, you're going to get this is a good projection so that the structure remains the same. I mean, just to say that you can have a silly projection where you get rid of one edge or something degenerates, and that is not good. But if you just project on the last 2 coordinates, this works. So let me draw the points. So there is 0, 0, this one. There is 0, 1. There is 2, 0. And then there is 2, 2, and 1, 2. So 2, 2, and 1. I might be doing something wrong. And 1, 2. Yeah. And so this is the. So this is the associahedron you're looking for. It is a pentagon, and this is how it looks after the projection on R2.
I have a question here. Could I ask?
I cannot hear you properly.
Could I ask a question?
Yes.
So, I mean, this is very far from being regular. In the case of, I mean, when we are in, when we look at a pentagon, all the triangulations are basically the same. So shouldn't we expect something regular? Wouldn't that be more satisfying?
Yeah, I mean, I don't know, you can choose a proper C to find a regular one, but this is not at all, this is not going to be regular in general, not at all. Yeah, it's just convex, and that is all we know. Yeah. So in fact, if you choose R3, or sorry, A3, and this orientation of A3, these are all the vertices of, or this is the associahedron. There are 14 vertices, and these are the coordinates. So these are the coordinates. The red numbers, so this is one coordinate. The red number, forget about the red numbers, those are the C's. The rest, like 0, 1, 3, 3, sorry, 0, 3, 4, blah, 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 these are the coordinates of the ones. And as you can see, this is not regular either. Okay. Yeah. So, okay, so where does all of this coming from? The answer is representation theory. So let me tell you about all these combinatorial objects that we defined and what is actually representation theory behind it. So the I plus, the smallest quiver that we had, that with the three vertices in that quiver, it's the Auslander-Reichlin quiver for representations of Q op. Opposite quiver only because I think this is only if you want left modules or right modules. I mean, yeah, you don't have to worry about that. But what is Auslander-Reichlin quiver? If you don't know, Auslander-Reichlin quiver is just, so this can be defined for any category. The vertices of this quiver are the indecomposable modules in that category. So in our case, it's going to be indecomposable representations of this quiver, and arrows are irreducible morphisms. So in fact, in I plus, all the 3 vertices in I plus were just the 3 indecomposable representations of A2. This infinite quiver that we built is the AR quiver for this bounded derived category. I is the not the smallest finite quiver, but the next one is the AR quiver for cluster category. You can all, if you don't know what cluster category is, that's okay. This can also be thought of some full subcategory of DB of this bounded derived category, and if you take its AR quiver, it's going to be I. So all these things are much easier to define if you just know the representation theory, but building representation theory is a little bit hard. So that's why I chose to do combinatorics first. So and if you know the representation theory, then you can already probably see everything. Then dimension vectors that we assign to each of the vectors or each of the vertices are actually just dimension vectors. If you remember, there were some negative values. So in I plus, the dimension vectors are really just honest to goodness dimension vectors of these objects in these categories. But whenever you see negative, these are actually the class in Grothendieck group of the bounded derived category. So if you, I'm not going to go into detail, but you can think of them as dimension vectors. And the compatibility is interesting. So as we said, the two vertices were incompatible if there was a rectangle, but two are compatible. So in the representation theory, it has a meaning. So ij corresponds to one indecomposable object, scale corresponds to another indecomposable object, and they're compatible if their x1s in both directions are 0. If you know a little bit about cluster algebras, then a compatibility just means that, so first of all, each of these vertices in I correspond to a cluster variable, and two of them are compatible. That means they live in the same cluster. That's all this means, but I'm not going to say too much about that. Okay, so now as you see, there is this whole combinatorics of representation theory that is embedded in associahedron. We defined a continuous associahedron just like, so we did exactly the same. So I will tell you the construction, and I will tell you like what you should think of in the finite case as we go. Okay. So to define the associahedron, let me tell you like the things that are needed. So first we define a triangulated category D, whose indecomposable objects are given by points in the strip. So I have this, I have the real line. I take the strip from pi/2 to negative pi/2. So all the points in the strip, each of them is an indecomposable object in this category. The points on these two boundaries are not included in the category. So because it's a triangulated category, I have to tell you what distinguished triangles are. Those are just rectangles. So whenever you see such a rectangle again, so again, this is exactly like the earlier case. So whenever you see such a rectangle or a tilted rectangle, you get a distinguished distinguished triangle like this in the category. Okay, so now, I mean, this is the infinite version of so how we built ZQ is this for us for continuous associahedron. Okay. I'm going to delete this because I will need it later. Okay, now remember how from the infinite version we cut a small quiver out of this. So we are going to do the same, although the small version is still going to be infinite. It's not going to be finite now. It will have infinite objects, but that's okay. So this is what we are going to do. We are going to restrict to a full subcategory. We are going to call it CZ. And this can be done by a combinatorial process that I'm going to tell you now. Okay, so I start with a zigzag on this strip. Okay, so let's start with, and by zigzag, I really just mean zigzag. Here you have some union of segments with slope plus or minus 1. Okay, so it's a zigzag here. Now I'm going to do something called quilting. So what I'm going to do really is I'm going to flip these arcs so 3 times until I get a reflection of this whole thing. So 3, because there are 3 line segments in this zigzag. So I will show you what I mean by the flip. So I am going to draw these rectangles or the corresponding diamond or rectangles here. Okay, this is one flip. The second flip would look like, again, completing the rectangles like these. Okay, and the third flip, I'm going to draw in blue again because that is the one that we want. Okay, so if my initial zigzag was called Z, the one that I get the third time after the third flip is the shifted one. Okay, and this is the CZ. This is the new full subcategory that I want. You can describe it using heart of the T structure and so on, but I won't go in detail. But if you know what all of this is, then this is the description for you. Okay. So anyway, what we have done is we had this whole infinite unending category. We cut a small full subcategory that is, so CZ is still infinite, but it's still a subcategory. And now our V, the ambient space, looks like this. So it's indexed by indecomposables in this full subcategory. So the associahedron is now going to be labeled by UZC. So it depends on the zigzag that we choose, and we are going to choose now the c-deformed relations. In the finite case, we only had I plus many C's. The tuple was I plus many C's, but now there are tiny rectangles everywhere, infinitely many ones. So what we are going to do is we are going to define the function C for every object in D and also 0. Okay, so so I mean, I'm really just doing the same thing because this is infinite. I have to do like all of this defining function and all of that, but basically it's the same concept. Okay, so I want these two things, and I want C to be positive for all X in CZ. So if a point is inside this region, the C corresponding to it, I want it to be positive. Just like we had positive values for the finite case. And I want this to be permissible. And that means that, okay, so the following. So suppose I have a tilted rectangle like this. I can cut it into 2 parts, and now I have 2 tilting rectangles, right? I can add the mesh relations corresponding to both of them and get a mesh relation for the bigger one, okay? But, and now this was okay for finite case because there were addition of finitely many numbers. But here there's going to be many, like infinitely many small rectangles everywhere. So first of all, we are going to have integration instead of summation because it's an infinite sum, and we want this to not collapse. So we want this integration of all these C's to be a real number. Okay, so this is this is what permissible means, that we choose this function so that integration over any rectangle x, y, z, w is finite. Okay, I can write this x, y, z, w. Okay. And then just like earlier, we have continuous version of c-deformed mesh relation. Again, it's the same concept, but because it's infinite, I have to do this function business. So I define this function phi such that for all rectangles, again, in our category D, I have that phi of x plus phi of y is equal to, and there is, remember there are c's inside, so I want integration over c of x, y, z, w plus phi of z plus phi of w. Okay, same concept. Now summation is integration because it's continuous, and yeah. Okay, so now we have the ambient space. We have the C. We have the continuous c-deformed mesh relations. We define associahedron exactly similarly. The continuous associahedron is sits inside V, and it's the non-negative solutions to this system of infinitely many equations. Okay. So here are some things that we proved and are useful to see, again, to see the associahedron. First of all, that it's a convex. I won't call it a polytope because it's something infinite. So this structure is convex. The second one, that there is again compatibility. So it's the same thing if whenever you can draw a rectangle and have corners x and y, left and right corners, then those are incompatible. Otherwise, you're compatible. So so you can again do something with maximal compatible subsets. Okay, so let me write this down. So for a maximal compatible set T in the subcategory, the corresponding solution, or corresponding solution where you assign, I mean it's the same thing, where you're assigning these things in the compatible set equal to 0. So the corresponding solution to this system is, so what we saw earlier was in finite case, these maximal compatible sets gave us points or vertices of the associahedron. It is not as strong, but this is on the boundary of the associahedron. So we don't actually get vertices, but it's okay. They're still on the boundary. And the other one is true that if if you have another maximal compatible set, let's say tau prime, such that t and tau prime, or tau and tau prime differ only by one object, then there is an edge connecting T and T prime, or the solutions of them. Okay, and I won't write this down, but yes, but we did prove that the infinite associahedron contains all the discrete ones. So the K2, K3, or the ones coming from type A2, type A3, all of them are inside they can be embedded inside the associahedron. I mean, the embedding is like vertices go to vertices, edges go to edges. There are some weird compatible sets. So just to give you an idea, a compatible set. So this Z is a compatible set. Okay, so this is something, one of the maximal compatible sets. Another compatible set would look like, you could have curves now because this is a continuous space. So you could have curves. So this is a compatible, maximum compatible set. But and for these we proved that they correspond to a boundary point on the continuous associahedron. But there can be some weird maximal compatible sets. Like you could have like infinitely many discrete points everywhere. They're not connected, but they could be discrete infinitely many points, and they could form maximal or just a compatible set. And then we don't know how to, we don't know what it corresponds to, or we know, but we couldn't show it. And another thing that we don't know is, remember how from R5 to R2, we got in the finite case, we found coordinates of points in R5, and then we said, well, we actually have, if we want to actually see it, we will have to project it on R2, and that's how we got the final pentagon. But in this case, we don't know what the projection should look like. So with that, I will stop. Thank you.
Thank you. Any questions?
Hi, so in the finite dimensional case, these realizations are, if you start with the associahedron and look at the normal fan, then these are polytopical realizations of the type cone of the normal fan, right? So is there similar interpretation in this continuous case also?
No, we don't know. No.
And just to make sure, these are infinite dimensional polytopes, right?
Yes.
Yeah, Pranav.
The projection is also going to be from infinite dimensional space to infinite dimensional space. So we don't know what is going to be.
I thought you said that the finite dimensional ones are sitting inside, but there's no way to sort of project onto the finite dimensional ones, the ABHY ones in this case, or maybe I misunderstood that.
No, what I mean is, like, all the finite ABHY ones are embedded in the infinite one. But so what I meant by that is the infinite or the continuous associahedron lives in this space whose dimension is huge, but it still lives in a smaller dimensional space. It doesn't, like,
the linearity space is still smaller than the space of the
but it's still infinite, so we don't know.
Hi, Maitreyi. Pranav
Hi.
here.
Yeah, hi.
I just had a question. So how much of this, the construction depended on this choosing a T structure in a category and so on?
Not really, because we just chose the T structure is really just this knitting process that I said. So the pause, I can tell you, the knitting is really you just start with this, and then, or not knitting, we call it quilting, because in finite case it's called knitting, and then because this was continuous we called it quilting. But so you start with this, and then you flip around in this, and this is what gives you the T structure. So D greater equal 0 is the positive part, is like you start at a zigzag and then you quilt forward, and D less equal 0 is you start at the shift and you quilt backward. So that's why the heart of the T structure is what lives in the middle. But that, I mean, but that is now fixed. Like it doesn't depend on the T structure anymore.
I see. Thanks.
Any other questions? Any questions from the online audience? You should be able to unmute yourself and ask. Well, I guess there are none. Okay, so let's thank Maitreyi again for a nice talk.